Jai Shri Gurudev. Dear students, in today's session, we will discuss about the block diagram representation for the control system along with the reduction rules in second module, which is named as block diagrams and signal flow graphs. Coming to the content, first I'll give you a brief introduction about block diagram representation, why it is important, and then you will learn about the block diagram pictorial representation for a given system and the reduction rules that is used to find the transfer function of a given block diagram. This is the outline of my presentation today. Now coming to the introduction part, a block diagram is a shorthand pictorial representation of the cause and effect relationship of a system. So in a simple form, if I want to define a block diagram, it is nothing but a pictorial representation of the operation what you are going to perform in a particular system. Okay, so the interior of a rectangular box here represents the block, and it is usually contains this particular block. This is the rectangular box which is representing our system, and it usually contains the description of the name of the element, or if with respect to mathematical operations, if I am building a system, it represents the mathematical operations to be performed on the given input to yield a particular output. And the arrows here, they represent the direction of the information or the signal flow for this particular system. So this is the basic definition of a block diagram. See, I'll just give you an example. Instead of just telling you that this is a particular operation, if I show you an image of that particular operation or a process, then it becomes easier for you people to understand the actual process. So for example, if I take a flower, if I say that there is a flower which is red in color, it has a stem, something like this, if I go on explaining, so you won't it takes a longer time for anybody to explain things, right? Instead of that, the image of the same concept, if it is sold, for example, if I'm defining a rose, so many things you need to tell. Instead of that, if I just show you an image, so directly you'll understand that I'm talking about a flower which is nothing but rose. So this is the basic importance of any pictorial representation. It makes a person at the other end to understand the concepts in an easier way. So that is why before building any system, we need to have a pictorial representation. The same thing holds good when you are constructing your house also. Initially, without planning, or we always go to an architect and we always plan, and you will take a pictorial representation of a building which you want to construct, and then only you'll go ahead, right? So that is what is the importance of a picture, right? So the same concept holds good in the control system also. So before building any of the control systems, I need to have a layout or a block diagram for that particular system, right? Now similarly, if I take some operations like addition and subtraction, and if I want to represent them in a block diagram form, so the block becomes a small circle called as summing point. So summing points are always represented using a circle like this. This is the pictorial representation what I'll be taking for a summing point with appropriate plus or minus. For example, if it is a summing point, if I'm performing addition, I'll be representing this with circle and plus. If it is subtraction operation, if I'm performing, I'll represent pictorially, I'll represent this with a circle with a minus sign inside. Okay, so here for example, let's take addition. Okay, I have two inputs, A, B, and if I give you a picture like this, easily you can identify that you are adding these two values. So I can take my output Y as equal to A plus B. So this is just a simple example I'm quoting for the block diagram representation. So any number of inputs you can give. For example, you can have two inputs, I can have three inputs. If I'm giving one more input here, then you can represent the same thing as Y is equal to A plus B plus C. Okay, so this is a simple example showing you how you can represent an addition operation using a summing block in the block diagram representation. So that is what is shown here. So this is plus plus, it is getting added here. So 1 plus and 1 minus indicates that you are subtracting here. And with 3 inputs getting added here, the output is taken as x plus y plus z. Another example is, so if I want to have sum of some inputs, so along with this summing point and other things which performs addition and subtraction, another two important elements I can call that is used in the block diagram representation is summing point and takeoff point. So what is summing point is nothing but, here summing point, as you know, it is going to add all the values. Takeoff point, what it does is it takes away the value for different branches like this. Okay, so one value could be allocated for different branches or different elements like this using the takeoff point. It takes away the value from a particular point in a block diagram. So this permits the signal to proceed unaltered along with different paths. So it can take any number of different paths and it can reach the destination. So that is the purpose of this takeaway or takeoff points. It is called as takeoff point also or takeaway point also, one and the same. Now coming to few examples what we can quote here. A1 and A2 are taken as the coefficients. Okay, so if I want to build a system which can perform this particular operation, that is x3 is your output, which is taken as a1 x1 of n plus a2 x2 minus 5. So x1 x2 and constant 5 are your inputs, where a1 a2 are nothing but your scaling factors. So this could be represented pictorially as a1 x1 a2 x2. You can take the value as 5, along with this you have to mention the sign at the summing point, and that is taken as your x of 3. This is one way of representation. Or else I just want to take the variables, if I want to separate my coefficient, then in that case you can take a scaling factor like this, where you can take x1 as an input for this scaling element, which is multiplying your x1 with a1, and your result is taken as a1 x1. So this can also be done. Okay. Now coming to the same example, it is represented using the scaling factor or scaling element a1 and a2 as x1. This is your scaling element which is multiplying a1 to your value x1, and similarly this is the second scaling factor or scaling element which is getting multiplied with the input x2, and constant is taken directly with the same sign as plus, plus and minus. This is another way of representing the same system. So these are other few examples where I can have a system output with a polynomial equation like this, where you can have n number of coefficients which are getting multiplied with the corresponding inputs, and they are getting added here. Now one task is given for us. Now you need to draw the block diagram for the given equation, that is x2 equal to a1 dx1 by dt. So that means I am taking the derivative of my input x1, and that is scaled with the factor a1. Then I am taking the integral value for x1 and I am then scaling it by a factor 1 by b. This is my first equation which should be represented in the pictorial form or in the block diagram representation. Now similarly, x3 is taken as a1 d square x2 by dt square, that is second derivative of x2, plus 3 into first derivative of x1 minus b x1. Now we'll try to represent them using the canonical form of the transfer function. So you can try those two. Now coming to characteristic equation, as you know, the one important thing what you should know when you are implementing any of your block diagram is your transfer function. So here output is taken as C and input is taken as R. So C of S by R of S is taken as G of S divided by 1 plus or minus G of S into H of S. So where G of S is considered to be the open loop transfer function, and this entire thing is considered as the closed loop transfer function. So if I am equating the denominator of the closed loop transfer function to 0, then that is called as the characteristic equation. Very important concept throughout this subject. Whenever if they ask you to find out the characteristic equation for a system, you need to just remember that if you are equating the closed loop transfer function denominator to 0, that is 1 plus or minus g of s into h of s to 0, that becomes the characteristic equation of your system. Now coming to the block diagram implementation. So let's take an example wherein we will try to find out the open loop transfer function, closed loop transfer function, control ratio, feedback ratio, error ratio, characteristic equation, right? So for this particular example, the open loop transfer function is g of s into h of s. The feed forward transfer function is c of s by e of s is equal to g of s, and control ratio is nothing but equal to g of s divided by 1 plus g of s into h of s, and feedback ratio is b of s by r of s is equal to g of s into h of s divided by 1 plus g of s into h of s. This one. Now error ratio is nothing but equal to e of s by r of s, which is taken as 1 divided by 1 plus g of s into h of s. And closed loop transfer function is taken as c of s by r of s is equal to g of s divided by 1 plus g of s into h of s. And the characteristic equation is 1 plus g of s into h of s is equal to 0. And the closed loop poles and zeros, if k equal to 10, can be evaluated for this. And now coming to the reduction of these block diagrams. Sometimes the given block diagram will be too complex to analyze. Okay, in such cases we need to reduce the block diagram into the simple form. So whenever a system is given, we may have a forward path, a feedback, so many inputs might be there. You might have n number of inputs. Okay, so we need to reduce our block diagram into a simple form so that you can find the transfer function for a system and you can analyze it. For that purpose, we are going to follow some reduction rules. Okay, so there are some standard rules which you will be learning now to reduce the complex block diagram to simplest form. Now this is the reduction technique. First reduction technique, what we have, combining the two blocks which is in the cascade form. So you can observe here that we have two blocks with the open loop transfer function g1 and g2. They are connected in a series manner or in a cascade manner. In that case, you can just combine these two blocks in a single block as g1 and g2 just by multiplying the two gains g1 and g2. So whenever you have two blocks in series, or you can consider that to be in cascade, then you can just replace these two blocks with a single block with a gain taken as the multiplication of the individual gains of the two blocks. So this is first basic rule. And now if the same two blocks, if they are connected in a parallel form like this, so in such case you just need to see what is the sign here that you have for the summing point. So if you have both plus, then you can replace this with a single block where you can add the gains of these two blocks since it is plus. You can take plus or minus because if I have minus, I can have minus here or here also left. Okay, depending upon what sign you have at the summing point, you just need to you can combine the parallel blocks like this. Now coming to the next rule, moving a summing point behind a block and moving a summing point ahead of a block. So if I have a summing point prior to a block with the gain as equal to g, then that is equivalent to what? If I'm shifting this summing point here after this particular block, then you can just replace the same block diagram like this. So you have to include one branch with a gain as equal to g. Whatever gain you have here, the same thing should be taken, and you have to include one block like this, and then you have to shift. Okay, so this is about moving a summing point behind a particular block. So there was a summing point behind your block g, and I have moved here after the block g. So then this branch will get multiplied with the gain g. And similarly, if I have a summing point after a block, so I have a block G and there is a summing point after this block, and if I want to shift this block behind this block G, so if you want to move the summing point behind the block G, then this branch, whatever you are shifting here, will get multiplied by 1 by G, or it is nothing but divided by G, the gain whatever you have for this particular block. So very important rules to reduce your block diagrams. Now coming to moving a takeoff point behind a block and moving up takeoff point ahead of a block. Pickoff point and takeoff point have the same meaning. So this is called as takeoff point, or it is pickup point. Now we have a takeoff point behind this block. If I want to shift this after this particular block, then this takeoff point should be multiplied by 1 by G or divided by G, the gain whatever you have here. Similarly, if I have a takeoff point after this block G, okay, and if you want to move this here before the block, in such case you need to multiply this takeoff point branch with the gain G. So as you can observe here, if you are moving your takeoff point which is behind a block after a particular block, then it is multiplication by 1 by G. Or if you are moving a takeoff point which was ahead of a block, then it is multiplication by G. Just try to remember like this. Now elimination of a feedback loop. This is called as your feedback loop, which has an open loop transfer function G and a feedback transfer function H. In such case, this loop can be replaced with the gain as G divided by 1 plus or minus GH. If it is if H is equal to 1, this is called as unity feedback. In such case, your feedback gain can be taken as equal to G divided by 1 plus or minus G. So you can eliminate a feedback loop by replacing the gain like this as G divided by 1 plus or minus GH. If H is equal to 1, then the same thing is represented as G divided by 1 plus or minus G. This is also an important rule in the reduction, block diagram reduction. Now coming to swapping with two neighboring summing points. That means I have a summing point which is named as A, and I have one more summing point which I am naming it as equal to B. The sign is plus and minus, so you can just swap your summing point like this. This is allowed. So you can first bring B and then A also. So both of them, they have the same meaning. Okay. So you can swap the two neighboring summing points if they are connected like this. Now let's take an example and we'll see how to apply the rules and reduce a given block diagram. So this is the system block diagram which is given to us with input as R and output as C. Now our task is to reduce this block diagram to canonical form. Now first thing is you have to check whether you have any series connection, parallel connection, and then you have to check whether you can eliminate any loop, and then you have to check whether you need to move your takeoff point or summing point to simplify a particular system. Now if you can observe in this diagram, the first easy thing that you can do here is we have two blocks which are connected in cascade. So you can apply rule 1 for this, and it could be just simplified as G1 into G4. This is the first thing what I have identified. Next part is you have a parallel connection here. So G3 is in parallel with G2 with plus sign. So you can apply rule 2 here and you can simplify this as G2 plus G3. So these two things I'll do first for this particular diagram, and I'll be simplifying like this. So please do observe here. So this cascade block is replaced with G1, G4, and this parallel blocks are replaced with a single block G2 plus G3. Now just identify what other simplification you can do. See, these two are not in cascade because I have a takeoff point here. So please identify here you have a feedback loop. So one forward path followed by feedback. So you can just replace this with your feedback loop gain. And then this becomes in cascade with G2 plus G3, and you have one more feedback loop and you can simplify. So we'll see that in later slides. Okay, so this is what I told you. You have a feedback loop, the G1, G2, H1. So that can be replaced with G1, G4, 1 minus G1, G4, H1. So since it is a positive feedback here, I'll have a negative sign here. So if you have a negative feedback here, you will have positive sign here. Just remember that. So because it is a positive feedback, I have a minus sign here. Okay. Now coming to the next part, when you replace this, feedback loop with the single block like this by finding the feedback loop gain, then this comes in cascade with G2 plus G3. So you can apply rule 1 for this, and you can simplify this as, you just need to multiply these two gains. So it is G1 G4 G2 plus G3 divided by 1 minus G1 G4 H1. Now please do observe here, this is becoming a loop now. This is your forward gain and this is your backward feedback gain. Okay. Now again I can apply rule number 7 and I can reduce this. So this is another example. So for the given system, you are supposed to find out open loop transfer function, feed forward transfer function, control ratio, feedback ratio, and so on. So let's try this. So first you have to reduce these two cascade connections. So you'll get this as equal to k divided by s plus 1. Then you will be getting a feedback loop here and you can combine it. And after simplification of this loop, you have one more loop which you can simplify. So first loop is this, which will give you the gain as equal to k divided by 1 plus k into s plus 1. So this is the reduction what I have applied for this particular loop, and k is taken as equal to 0.1. So further if I simplify, so these are my open loop transfer function, feed forward transfer function, ratio, error ratio, and so on, what it is represented here. So you can solve this. In today's session, we have discussed about block diagram representation of control system, why it is important, and how you can represent a given control system using the pictorial representation. And you have learned how to reduce a given complex control system into a canonical form by applying the different rules. So as discussed in rule number 1, you have learnt about cascade rule, where if you have two blocks which is connected in a series form, then you can just multiply the gains. And in the second rule, you have learned if the two blocks are connected in the parallel form, then we can just eliminate that block by just either adding or subtracting the two gains depending upon the sign what we are going to have for the gain. Then in the third rule, you have learned how to shift a summing point which is before a block, and how to shift a summing point after a block. So this is your rule number 3 and 4. In rule number 5 and 6, you have learned how to move a takeoff point which is before a block and which is ahead of a block. And in the 7th rule, you have learned about reduction of the feedback loop by using the open loop transfer function G and the feedback transfer function H. And few examples on this were shown to you in today's session. So try to take a different block diagram representation like this and apply the reduction rule and try to simplify the given block diagram and evaluate the transfer function for a given control system. So these are my reference books from which I have taken the problems. I hope today's session was informative and you are able to understand the reduction rules in a proper way. Thank you all for joining the session. Have a nice day.